Yeah, these days in the media, I think everyone's trying to be unbiased now, right?
Yeah.
Yeah, we're not going to do that. This is in my biased opinion.
Welcome. So today we'll be talking about inference, quantization, pruning, optimization in general, maybe some low level like memory layouts or what is a static graph, dynamic graph, different quantization patterns.
We're going to talk about a lot of stuff.
Yeah. Talk and talked.
Yeah.
This is like that movie.
Like Looper?
Yeah, Looper, what is it?
Tenet?
Tenet.
Yeah, Tenet.
Yeah. There are so many flavors to quantization. You will hear so many buzzwords. Static quantization, dynamic quantization, hybrid quantization, GPTQ, AWQ, or what am I missing? Yeah, quantization aware training.
Quantize means you go to integer space, right? We
Yes.
should explain that. So if quantize means you're going into integer space and integer space is fast, then you want to turn from float to integer space really early. You want to stay there as long as you can, and you want to put off going back to floating point until as late as possible. That will give you better inference performance. Is that fair to say?
Yeah. That's super accurate. So in Onyx, there are two ways to represent quantization. You would have something that is called tensor-oriented quantization, and there's operator-oriented quantization. And well, some frameworks go with operator-oriented quantization in general for a lot of formats, and others prefer the tensor-oriented. In my biased opinion, the tensor-oriented is better because it's just a way of adding hints to whatever graph compiler would take this file. It will be like, hey, it would be great if you can take this and fuse it into a quantized node. And on the other hand, if we force, for example, a quantized operator, a native one, then those graph compilers may not understand what this operator is. However, if we say, hey, here's a conv, and here's a QDQ node, which is a hint that, hey, you can fuse this if you wanted and make this quantized. If you're doing the other one, it's Q linear conv. And that thing is just, okay, well, I don't support this operation. I don't care about it. And the tensor-oriented just more general purpose.
Right.
And how would you encode the quantization information in that, for example?
Well, we have QDQ nodes, right? And each of them is going to have like a scale and 0-point pairs. And like those scale and 0-point pairs is going to basically represent how this activation value is going to be, or weight value is going to be mapped into the integer space, right? And one of the problem with the QDQ format that we had lots of trouble with was that like depending on where you put QDQ nodes, your model might actually slow down. So even though like things are happening integer or like float point, whatever, the model is slower than the original one. And that is because like of how this QDQ nodes propagate. As Ben said, QDQ nodes are basically a hint of like how you should fuse the models, right? So sometimes your QDQ models can propagate backward or forward, fusing into like other nodes. For instance, like if you have a ReLU, for instance, and then there's a QDQ before and QDQ after, those QDQs might like fuse to the convolutions above or the max pool like below, right?
Yeah, there are a lot of ways. So like we have literally, when we say QDQ, it's quantize node, and then dequantize, and then maybe an operation. But the idea is you're trying to maximize the quantized computation as hard as possible. So you're taking this Q and you're pushing it as high as possible, that everything would be affected by it, and taking this dequantized and pushing it down as low as possible. Just trying to maximize as much as integer computation. And there are lots of restrictions in general. Like frameworks have their own quirks. I mean, a lot of companies that develop their software solution for compression and whatnot actually go the wrong path, in my opinion, and they go with operator-oriented, while the tensor-oriented is just more healthier. Because technically, you can, even if you you don't do the QDQ, you don't apply it, you can still get really good performance, or maybe just ignore it for some things. It's just more healthier than trying to force more things to parse. Like then you start asking, how do graph compilers work in general? Like, okay, well, they're taking a file, some structure, and they're trying to map this into operations they have.
Right, that's right.
And I mean, just adding the overhead of very niche operations like QLinear conv or something, instead of just doing pattern matching. Hey, here's the QDQ, here's the conv, bam, done. I want this in, I don't want this in, but it's easier, I feel like, than dealing with niche things.
Right.
Because it's just literally a plain vanilla conv with a QDQ, Q, DQ.
But the point is that like, even when you've done all these optimizations for inference speed, you still need to be running on the right hardware.
Yeah.
Right? Like you need to have a device that's actually matching the operations that you're trying to do in the quantization scheme that you've chosen, which is, I think, something that maybe a lot of practitioners don't actually do in practice. Like they run through all these quantization pipelines and then deploy it on the wrong hardware.
Yeah. And then they're seeing bad results and they're like, oh, why doesn't it? Why it's not fast?
Yeah, and because it's not easy, it's not obvious. Yeah.
It's annoying a lot of times. It's really annoying to get right. I think I remember like this saying, quantization is like printers.
Really?
Yeah, when quantization
That's
works.
not fair to quantization.
Yeah, no, it's not. But when it works, everything is good.
Yeah.
When it doesn't work, everything like just horrible.
Yeah, and it can disappoint you in like really mysterious and strange ways. Yeah, and that kind of goes back to what we were talking about in the last episode, where it's like how you develop a lot of these algorithms is usually not the same environment that you're actually deploying to. So even when you've done all these inference optimizations and stuff like that, it's good to actually be able to test it in some way on like the architecture and the environment that you're actually going to be running it on, which is, of course, when you need to build something really fast, that's exactly what they do. They're constantly testing it on the hardware that they're going to be deploying it on. But most people developing models are kind of like more casual about it, and they don't have that development pipeline. They don't have that luxury. So it's nice to have a seamless tool that can do it for you, I think.
I think that's part of the difference between research and actual, like, getting done.